president of the National Academy, and then a keynote talk on what's happening in engineering education. So I'm going to simply introduce Dan Mote, who is the president of the National Academy of Engineering. And so, Dan, welcome.
Thank you very much. Well, thank you very much, Leah, and I very much appreciate this opportunity to come here, and I get to make a couple of remarks and then introduce Darryll Pines. I really want to thank the committee for this project, for this work. Probably a lot more than you might imagine, as a matter of fact, and Leah, of course, for taking this on. As you may know, I can't remember what you heard yesterday. The National Science Foundation specifically asked for this project about the engagement of engineering societies in education, and I suppose undergraduate education, but actually I think, as a matter of fact, all education. Now, it's not an entirely new idea to have engineering societies associated with education. If you look back in history, I can always remember engineering societies are very key to the whole thing. But in a more organized way, having more direct responsibilities, then you think, of course, the first thing you think about is undergraduates, young people, but it's actually the engineering education part is also for those people who are transitioning. More and more people are changing jobs, getting new jobs, and new areas coming along, and so forth. And we as a nation do not have a mechanism for re-educating this population. It's one of our greatest deficiencies in engineering education, to my understanding. There's everybody knows, everything's accelerating, things are going faster and faster. People are changing jobs more often, and the jobs they're going to be changed to are not ones they have preparation in. So therefore, how are they going to get tuned up so they can actually contribute, have a successful life and family there? So in other words, we have to expand the teaching workforce here to handle this population, which is not going to be small. It is, in fact, not small. Therefore, it naturally comes in that the engineering professional societies could play a significant role here. So there's a lot of dimension to this discussion, from my point of view. Not just normal, educational cycle that we think about, but the transitioning cycle for all these new people that need education, and that where there's a lot of capacity in the engineering societies. So this workshop really is the kind of second chapter in this project, designed to really provide the opportunity for engineering societies to kind of share information with each other, both current and planned, to explore ideas about how societies can have a more effective role in engineering education, and also to consider actions, move forward, those coordinated and uncoordinated as well. So yesterday you had a full day, I understand. I was occupied. I'm sorry about that. I apologize for not being here. I was just coming back from the UK. But you talked about what engineering societies are doing and what societies are learning from each other. And then today, it's about what societies can do together and actually do for engineering education going forward. So it's all about students, right? Old and young. It's all about next generation engineers. That means next generation problems. It's all about problems for today and tomorrow. It's all about creating talent. Everybody, every organization, every country, everybody on the planet is hungry for talent. That's the one consistent theme you get wherever you go. Talent is the coin of the global realm. And the Chinese are looking for engineering talent. They have more engineers graduating in China than the rest of the world put together. So this is a huge problem, and that's where, of course, the professional societies come in. Now, to continue this discussion into this next chapter, we have to really look at the engineering education part, not just how the professional societies could work together, but what's the education part. So you really need a kind of education expert to say a few things about this. And so we really have an opportunity here for you to learn about this, to discuss the understanding of how engineering societies can best serve engineering education today from the engineering education point of view. So our next speaker is really ideally prepared to address this evolving picture connecting engineering education to engineering societies. It's Dr. Darryll Pines. He's the Dean and Nariman Farvardin, we would say, from Iran, Professor of Aerospace Engineering at the University of Maryland. So Darryll brings a perspective on this topic really is honed by a long and dedicated blending of leadership in engineering education at Maryland's Clark School, but with his dedicated work with professional societies and foundations, including ASEE, ASME, AIAA, Sloan Foundation, DARPA, and so forth. So he's got a wide span of experiences. His deep commitment to engineering talent in engineering education and in K through 12 STEM education as well are built around excellence, innovation, diversity questions. All are critically important to all of us and certainly to education. And that will provide the workshop participants with a current and wide-ranging view of the state of engineering education. So as dean since 2009 at Maryland, his impact on the university has been tremendous. He's improved teaching in fundamental undergraduate courses, raised student retention rates, competed and succeeded in national and international student competitions at high level. It's a high priority for him. Placed emphasis on sustainability engineering and service learning, promoted STEM education among high school students, and increased the impact of the research programs, of course, as well at the University of Maryland. The university's solar decathlon team placed first in the world in the most recent DOE competition. Its Engineering Without Borders chapter is long been one of the world's most active and best, and the Engineering Sustainability Workshop launched by Darryll has become a key campus event. He has testified before Congress on STEM education, created a top 25 source schools program for all Maryland's high schools. At the national level, he's held an effort as part of the ASEE Dean's Council to develop a College Board AP exam in engineering. He even roped me into that, as a matter of fact. He is a current secretary on the executive committee of the National GEM Consortium, a national nonprofit providing programming and full fellowships to support increasing the untapped domestic human capital at the graduate level in STEM fields. Darryll's been director of the Sloan Scholars Program since 1996, serves as chair of the Engineering Council of that program. He currently serves on the Executive Advisory Board of Engineers Without Borders. During a leave of absence from the university in 2003 to 2006, he served as program manager for the Technical Technology Office and Defense Secretary's Office of DARPA. While at DARPA, he initiated 5 new programs in 3 years, primarily related to development of aerospace technologies, for which he received the Distinguished Service Medal. He also had earlier positions at Lawrence Livermore, Chevron Corporation Space Tethers, Inc. His academic record in aerospace is stellar. He currently focuses on structural dynamics, including structural health monitoring and prognosis, smart sensors, adaptive morphing, biologically inspired structures, as well as the guidance, navigation, and control of uninhabited space vehicles. He's, of course, a fellow of various institutes, Institute of Physics, ASME, AIAA. Now, in 1982, while I was a member of the Berkeley faculty at the time, I was the academic advisor to a freshman ME student named Darryll Pines. So after 4 years of my advice and not taking it entirely, he left for MIT to earn a PhD in ME in 1992. In 1995, he joined Maryland as an assistant professor of aerospace. And in 1998, when I moved to Maryland as president, I knew only one person on the campus that was an assistant professor in aerospace engineering. So with that, I welcome Darryll Pines here to really enlighten everyone on the engineering education business.
It's funny. I didn't know you were going to say that. I didn't want us to know that really detailed story about you and I. It's funny. When you have someone like Dr. Mote, who's your freshman advisor, and even you don't know when you're 17, 18 years old that your paths will cross some 20-something years later. And it's been an honor, to serve and witness his career and for him to be a mentor of my own career. So thank you, Dan, for those kind remarks. So I thought, I was asked by Leah, a good friend of mine, and Reed and the committee to talk about the evolving engineering education. And I know I have to stay next to the mic because people are online. So this is sort of going to be my perspective, but I know there are many colleagues and friends in the room who also have a perspective on this rapidly changing educational shift in paradigms. So make sure I get this right. So here's what I'm going to talk about. This has to be the heyday of engineering. So I'm just going to give you a status update on engineering enrollment in the world and in the United States specifically. And then, part of how we frame ourselves is the definition of what is engineering. And then, of course, I'll talk about the history of engineering education over the last 150 years. And then the evolving learning paradigms that you all are participating in with me as well. And then who are we educating? I know that Dan mentioned, obviously, transitioning engineers who always are having lifelong learning. But we're dealing primarily with young people who are the Millennials and the Gen Z. And then, of course, the emergence of online education in general and online engineering education specifically. And then challenges facing the future engineering education enterprise. And, of course, I'll end with the connectivity back to this workshop. So look at this. I mean, this is amazing. This is the last 17 years of engineering enrollment in the United States. It's just an incredible growth period. All of my colleagues who are in the room who are academics, who are chairs or deans like I am, know what I'm talking about in terms of the enormous impact it's had in our programs and the quality of the students that are coming to our campuses and so forth. And so this is probably the heyday of engineering. It's a great time to be an engineer. It really is. You all know that. It's exciting. It's exciting to have this kind of excitement about our field. So that's why engineering education is so important, because of these enrollments that we're seeing at our various campuses. And so just look at sort of how the demographics has changed just slightly. I mean, so there is some positive perspective here. And so we see that, just 10 years ago it was 421,000 total engineers in the United States enrolled in engineering courses, and now it's 700. But we also see that the female population is growing accordingly to the enrollment growth. And all the other demographic groups are growing now. Unfortunately, African-American groups is not growing as rapidly as, say, the Asian-American or the Hispanic-American. And there's also an increase in universities and foreign students coming to our campuses now. Partly somewhat driven by lots of factors, and some might say financial as well. If we look at this from a demographic of the United States, this is that upper chart is a census chart. And so you can see that the light blue are Caucasians. The dark blue are Hispanic Americans. The sort of upper reddish orange color are African Americans. So those are the percentages, and you can just see it over 100% over time, going towards 2050. And then you can see what it is for engineering. This is just those same numbers now computed to be engineering. So if you take out the foreign students, and this was shocking to me, to be honest with you, I took out all the foreign students of the recent ASCE data. And actually now we're at either 22.9 or 23.1% female. I found that actually shocking, because we've been historically at 19%, for a very long period of time. So it's really starting incrementally to go up over this last decade, which is nice. African Americans are still hovering around 5%, have been higher in the past. Asian Americans higher than their population average in the census. And we see a large growth, I think, in Hispanic Americans going into engineering. So this is good that the diversity is increasing. And so you see that the Caucasian numbers have come down to 57.4%, with time. So we're becoming more balanced. We're still not there, obviously, by any stretch of the imagination, but the demographics are slowly moving. So what's happening in degree productivity? Real quickly, we have produced 80,000 BS degrees in 2005, and now we're over 100,000 because of this huge enrollment push. And also our retention and graduation rates are going up because of the things that we are all doing in engineering education, which is quite nice. But the burden to the faculty member has gone up as well because of the sort of funding, state fundings at most of the large publics, and also the concerns that even at privates, is that we don't have as many faculty members to service the large enrollment. So you have 4 degrees being graduated per tenure track faculty member, and then the average students per tenure track and this is all public and private, has gone up from 17 to near 25, so almost by 8 students, right? So there's been a burden as well on the faculty. Now here's the best part. Our people are getting jobs. It's wonderful to be an engineer. It can't be any better. These are the top 15 majors 2016, 2017 on payscale.com. The red ones are, I would call, the non-engineering majors, but computer science is embedded in there. I'm surprised computer science wasn't at the top of the list, to be honest with you, because I know our students have been getting $90K salaries, so I'm just surprised it's not at the top of the list. But these are the top 15 payscale.com salaries, for entering into the workforce. So we deliver, students who get jobs who go directly into middle class or upper middle class, depending on how much money they get. I mean, it's pretty a neat thing. And even all that volume, with all the people that are graduating, people are getting jobs. So placement is good. It's a great time to be an engineer. I think you know that gentleman there. So what is engineering? I think this is what frames how we teach engineering. This is ABET's definition. So I'm going to read it so you all remember it. The profession is in which a knowledge of the mathematical and natural science is gained by study, experience, and practice is applied with judgment to develop ways to utilize economically the materials and forces of nature for the benefit of mankind. That's a mouthful. Does that get you excited about engineering? Not really. So Dan likes us to think about it this way. Engineers create solutions serving the welfare of humanity and the needs of society. Simple, tight, creativity is emphasized, humanity is emphasized, society. We're the only profession in the world that people don't know what we do. We can't communicate it to ourselves even. If you look at the definition above it, we can't even communicate it to ourselves. But I think Dan has come up with a way to frame it. Creation, solutions, humanity, and society. And if we just take that and fold it into our framework for engineering education, we'll be able to really communicate what we do to the general public and also to the students that we're educating. Now, let's talk about the history. How did we get to where we are today? This is the first half of the 19th century. And essentially, like many things in our country, was driven by the military. So the creation of the Army, the U.S. Army, more importantly, infrastructure projects created by the establishment of the Army Corps of Engineers at West Point, New York. The first time there was an engineering course or curriculum that was established. And formally, the programs actually started in 1817. And then as that started to emerge, civil infrastructure became sort of like the first founding discipline of the field of engineering in the United States. Of course, engineering has been around for thousands of years, but in terms of formalism for the United States. And a university called Norwich University gave out the first instruction in civil engineering, and then RPI followed sort of the models from the French, and that's how these institutes also started to emerge sort of in the early 1800s. These were the three first programs. And then the big push came with the Morrill Act. You all know that. I'm at a land-grant institution. Many of my colleagues in the room are at land-grant institutions. And this was the biggest push that really solidified the fields in engineering and education at the beginning, of our field in education. So it was the second half of the 19th century. 1862 was the signing of the Morrill Act, and all these universities emerged as land-grant colleges across our country. You can see there's some gaps in that chart in certain states, which is kind of interesting in its own right. And then there was another passage of the extension or amendment to the Morrill Act in 1890, which opened it up for HBCUs. And that's when most HBCUs started. So either schools are 125 years old or roughly 160 years old. That's where most of the big land-grant colleges are. And, of course, the privates started somewhere around this time as well. In fact, Cornell was one of the original land-grant institutions, but it's a private institution. And, of course, that's James Morrill there in that photo. So now, based on this beginning, hundreds of engineering schools were started. So what I would like to just show you is just the evolution of engineering education as I sort of gleaned from various journal articles, talking to a lot of people for this talk. And essentially in that second half century of the 19th century, it's primarily focused on practice. There wasn't a large curriculum ready for that. There was not a large theoretical focus. It was shop and foundry skills. So you can go back in your own archives of your own land-grant institutions and go through the archives and see how education was done back then. Primarily it was done to help manufacturing in the United States, believe it or not, to get people trained to go into the workforce just as we were doing today, but in a different way, more with technical hands-on skills and a connection to practice. That's why infrastructure was first. That's why you see on this chart that the American Society of Civil Engineering was the first professional society. 1852 was its start, 1852. Followed by American Society of Mechanical Engineers, and of course now adopting standards and codes. right? And then we see the evolution of now more of a focus on curriculum through the American Society of Engineering Education beginning in 1893. It's actually very interesting to see this history. Thurston was at Cornell and came from a military environment and therefore instituted more training related to foundry skills and shop skills. Then there was this shift to theory and science for about 50 or almost 60, 70 years. And this is driven by also the climate in the world at the time. World War I was between World War I and World War II. Several European scientists left for Europe, including von Karman and Timoshenko. Timoshenko went to the University of Michigan first before he went to Stanford. Von Karman, of course, went to Caltech. And these became two prominent theoreticians in mechanics and fluid mechanics in the world and in our history of science. And therefore, this caused a shift into more of a mechanics focus of theory and science in the curriculum of engineering education. Then you see ABET emerging in 1932 to help establish some type of standard for the curriculum that was evolving, focused on the theory, but to achieve some level of what is the quality standard by which we're going to measure these programs. So that's when ABET started. Then as we get closer to where we are today, we saw the focus on engineering design, project-based learning, taking the trend back or swinging the pendulum back from theory and science to more practice and hands-on engagement, but with very focused local projects as opposed to more global projects. And then also on ethics and professional development. During the same time period, or just at the end of that time period, it was when ABET in 1994 had a workshop to really look at the curriculum and how we're going to get student outcomes, develop new criteria. And that actually went on for about a 6-year period before the EC 2000 criteria came out, the big A through K that we all have been working on for many, many years. And then, of course, it was tied to continuous improvement. And that leads to where we are today, which I believe I call modern engineering education. We are now added the concept of research, the concepts of complex systems, pedagogy, active learning, service learning, online education, virtual labs, and of course innovation and entrepreneurship. And this new era has been driven by the focus on research. And thanks to Leah's leadership and others in engineering education, she was the first to launch departments of engineering education, and now there are 4, and I believe there are going to be 5 and 6 emerging in just another few years, if not already done. And so this is a paradigm change. This didn't exist before, that there was research focused on learning and on engineering education to improve the enterprise of education. And so that's how I see where we are today. Now, what has been the major paradigm shifts according to this history? Well, pre-1950, in my opinion, was focused on engineering practice, designed according to codes and well-defined procedures, limited use of mathematics. Many faculty were industrial experienced and or strong ties to industry. The next era was focused on engineering sciences. You remember there were departments of mechanics. They don't even exist today. It's amazing. They've almost all gone away. Right? It's amazing. That was the theoretical portion of our field in education. Fundamental understanding of phenomena, analysis, majority of faculty trained from the academic research, less from practice. Almost to currently, focus on project-based learning. This was supported by a number of entities, NSF, lots of foundations, Sloan Foundation. Lots of schools went in this direction to encourage teamwork, communication skills, the integration of engineering and systems engineering. Design was a focus, manufacturing, continuous improvement from ABET, and maintain that strong analytical base as well. To where we are today, which I believe we're still in this paradigm shift, we haven't really evolved to a steady state, with the focus on active learning, experiential hands-on activities, again, the basis of teamwork, obviously communication skills, design, but now we see creativity and innovation coming into play. Not that it wasn't there before, but there's more of an emphasis and focus and curriculum associated with it. We also see project management as a key area, management and leadership in general. We have definitely all embedded ethical reasoning into our curriculum to make sure that our students have that concept understood when they make their decisions. but now we're also doing things in a global contextual context of analysis. And now we are incentivizing our faculty, rather than just awarding tenure-track faculty for their research, we are now incentivizing and rewarding faculty for their teaching expertise and contributions, both in research and in teaching. And so we see that pedagogy will eventually affect what we do. It hasn't made it there yet, but it's moving in that direction. So this is still evolving, but it's quite exciting. So where did this need for change in engineering come from, in engineering education? There have been numerous studies here at the National Academies, but one of the earliest studies was a Mann report from the Carnegie Foundation that took a really comprehensive look at that first era of engineering, sort of the 1850s to the 1900s, and that was, again, remember, driven by practice. And if you read this report, it's how we actually moved into the theoretical side of the house, and it sort of made some recommendations. And then to where we are today, the National Academy's report on the Engineer of 2020. So if we look at this, this was like the first picture of civil surveying engineers, believe it or not, from Rutgers University. And it was more, of course, focused on practice. Anybody from Rutgers in the house? No. Okay. Now, we've gone from this, which is practice-based, and this next picture is also practice-based. I wouldn't say it's a good practice-based, but actually using humans to actually measure the impact of materials for helmets against the side of a wall while 3 scientists are observing this poor human do this. I would say that was too far of the pendulum going to practice and putting the human in the critical path, which was absolutely unnecessary. To this, which is Virginia Tech's work on impact and concussion and new technology for minimizing concussions on athletes who play this sport of football. To this, where innovation now has come in through Dartmouth on the robotic moving tackle dummy so that we can minimize the injuries to athletes going forward. This is all engineering. And I'll give you the example because you can relate to sports very well, like most people. But this is all where we have come, from practice to theoretical analysis and testing to innovation, where we are today. And so, but it's been driven also by, to ensure U.S. competitiveness, right? As Dr. Mote just mentioned, we're in a worldwide competition for talent. That talent could go anywhere. It could stay in the United States. The innovation can stay in the United States, or it could go somewhere else. So these studies were not just done to improve engineering education, but it's improved the ability and economic viability of the United States and its workforce. And so I just give you these examples just to paint a picture. So what were some of the forces driving this change in engineering education? Engineering colleges and departments and their advisory boards, we all have them at the college level, at the department level. Engineering professional societies, like where you all come from. I didn't mention all of them. If I did, the whole page would be full. I just gave a few examples. The National Academy of Engineering, thank you for the Academy's leadership. Numerous studies demanding change to serve the welfare of humanity and society. Numerous studies. We just haven't been responsive enough. National Science Foundations, obviously, programs, workshops, studies, roadmaps. Now we have an entire roadmap for engineering education with the science background behind it. It's fascinating. It's great. It's wonderful. Industry and private foundations. Let's not forget these. The Kern Foundation has funded a number of engineering education studies. Ford, Bechtel, Chevron, Olin. That's how Olin College was started, in fact. Gates, many others. Obviously, ABET. We are grateful to ABET. I have nothing negative to say about ABET. Nothing. Only positivity. Thank you for trying to improve the quality of all of our programs. EC 2000 really made a difference. I think it really got us to think deeply about our field and think out of the box. And now, more recently, we see that it's not just engineering, education, research. We see that facilities are paramount to change as well, and technology through information technology. So now we see the congruence of these three things: research, the facilities that do them, technology, and of course, the people who actually make it happen. And that's what's been going on. Information technology, online education, flipped classrooms, maker spaces. Almost every university now have open maker spaces for not just their engineering students, for all students. Open laboratories to let students just do what they want to do. advances in engineering education research that are happening at the 4 departments that exist, but also across the country. It's fascinating that this is now coming back into the learning methodologies. So we have a complex task. Modern engineering is increasingly complex, so therefore that makes engineering education challenging. Smaller and smaller, larger and larger, faster and faster, more and more complex and system-related, and then to have great societal complex. We've all been dealing with this in our research domains, nano, bio, info, and also the macro domains, energy, environment, manufacturing, communications, logistics. But they've superimposed that we've got to educate our students in natural sciences as well while we're doing these other things. We now have to bring in the social sciences and medicine because of the congruence of field, and engineering ties it all together. Then we have to think more systems-oriented to actually develop large-scale systems and have people be able to model them. And then more recently, we see the emergence of a broad new field that is so big we can't even imagine where it's going, data science and analytics, that it's coming in to help do several things. You can imagine now mining a particular topic that will help accelerate research breakthroughs because you're doing the appropriate data mining and machine learning to actually figure out what are the proper directions to go. So this is just an emerging thrust that we need to wrap ourselves around as we do our engineering education as well. So it is an exciting time period to be an engineer, to be in the education enterprise, and I'm grateful to be here with you. So what have we done, though, to respond to these changes? So this is sort of what most of us have done. This is a broad sort of statement. We have created a multi-year, vertically integrated, sort of hands-on, experiential learning kind of curriculum structure, right? Where we all now, most private and public engineering schools, as they take in the income, which is the K through 12 student typically, and we do take in older students as well. We take in students from community college, usually through the second and third year. So there's input here, but most all of us culturally, to connect students to the field of engineering, have created an environment that first we call it the first year experience, right? Some of us do a design experience, some of us do other things that are more team building, really cultural building to make sure that these students who come in, they have great science and math skills, but now understand the field of engineering, understand what it can do for society, but more importantly, build a culture of conclusiveness as well. And we all are doing this. What has been wrapped around it are all these other things. So now we have maker spaces. Now we have been integrating possibility of design thinking, which is sort of a Stanford design studio sort of approach into some of our even engineering design classes. We have shops and novel classroom environments that we didn't have maybe a decade ago to do flipped classroom environment, blended learning experiences, right? We then tie back to you, the societies, through many different modalities. So we do, obviously, through internships and co-ops, but now you're tied into some of our innovation and entrepreneurship. Some of you are entrepreneurs in residence with us and providing advice to our students. Some of you are providing capstone sort of problems as an advisor to our first, second, or third, or senior capstone design experiences. And then you're helping with licensure. So you play a role in this entire vertical integration of our curriculum. And I'm not going to go into any details in terms of the requirements, but this is roughly the structure that most schools tend to do. Here's the things that have been wrapped around it as well. Unique experiential learning. We didn't have hackathons 6 years ago. Nobody even knew what a hackathon was. We all do hackathons now. It's amazing. But why are we doing this? There's something else going on, right? There's the revolution in computing. And don't turn a blind eye to that. In our Department of Computer Science at Maryland, there's 3,000 students in that department. My college is 4,200 students. This has only happened over the last 3 or 4 years. I'm sure it has happened in your school. We cannot turn a blind eye. This is a different revolution than the dot-com revolution. This is a revolution that engineering folks need to embrace and incorporate into what we do as well. So that's the other thing, and that's where the hackathon's coming from. Student competitions and challenge prizes, all of us have, our students do them, but I think they really provide this outside the classroom learning environment that really gets them doing real engineering, real project management, and every now and then a successor to. And of course, because of our students and their focus on social issues, the service learning has become paramount for us to do in community engagement. So these are the other things that we are doing to engage this population. Now, with all of that said, we are all tying this to ABET's continuous improvement process, right? So we are always constantly reviewing our programs and constantly looking for those student experiences to enhance the learning outcomes so that our students exit and go to corporations and do really well. And so the EC 2000 is that framework that we have been really tied to as well. So I don't want anyone to think that it's not embedded in everything that we do, but of course it is. And of course professional societies play an enormous role here. Now at Maryland, we created a program called the Keystone Program. And we essentially saw these things happening with project-based learning, active on hands-on learning, and decided to focus our first 2 years on this sort of wonderful cultural engagement of the field of engineering for those students who maybe have never even picked up a hammer or picked up a screwdriver, and they were afraid to tell you that they never picked up a screwdriver or a hammer. And so essentially to incentivize our best faculty, so this is now reward faculty for teaching and educational innovation, and actually give them even titles of a named professorship for instructional and tenure track faculty who teach in these first 2 years. Improve the instructional facilities to accommodate this new generation that wants to do these sort of engaged learning environments, and provide, of course, sufficient technical staff support, and encourage an active hands-on learning environment, and also have embedded in the experience team competition. And then use mentors, which we call undergraduate teaching fellows, who are third and fourth year seniors for the first and second year students. And then use the societies through professional engineers to serve as advisors of these teams inside the classroom, mentors, and of course to review critical designs and preliminary designs. This has gone very well for us. And just as demonstrated by the retention and completion numbers here, we are now at a 6-year completion rate of 75%. If you come into engineering, graduate 6 years later at 75%. That 90% number is, if they leave engineering, they graduate at a 90% total plus engineering and somewhere else in the university. I mean, these are very high for a public university. The national average for public and private, by the way, in completion rate is 59% for 2015. And so we've talked with Greg from UC Irvine about this program, and Greg has modified it to customize to what he wants to do, and for other folks at other schools. And so this has been a wonderful way to embrace all the things I said before, but also have it yield results in your outcomes. Now, we do things as well, thanks to the National Academy of Engineering, in context of societal's grand challenges. So we are grateful that in 2008 that the National Academy of Engineering chose these 14 grand challenges to focus our energy in engineering education as well as in research on these grand challenges for society and for the world. And with that, Dr. Chuck Vest, who was the predecessor of Dr. Mote, essentially came up with a Grand Challenge Scholars Program, in which it was a global grassroots program encouraged and supported by Dr. Vest. Each school's program includes curricular and extracurricular activities designed to give students skills and experience in 5 required areas: research related to the Grand Challenge, multidisciplinary experience, the global dimension, entrepreneurship, and service learning. To date, there are 36 universities, U.S. universities, and 4 overseas universities who are participating in the program, and 80 others have actually committed to participating. This is a way to connect the field of engineering and what we do in creation and solutions and humanity and society to the actual problems that we're trying to expose students to solve. And so it's a wonderful program. I know Dr. Mote supports this program 100% and would like to see more growth at U.S. universities. So what are some of the common desires that we're trying to impart to these students? Engineers are problem definers as well as problem solvers. We want our engineers to be flexible, better able to straddle uncertainty, risk, disciplines, cultures, ethics, evolving technologies. They always have to be prepared for that. That's what we do. We engineer technologies. Engineers prepared for creativity now. This is the best thing about our field. People don't know that our field is so creative. I talk to so many people, I'm sure my fellow colleagues talk as well, and they don't know how creative this field is. It's creative. You can come up with anything. It's unbelievable. Innovation, business management, entrepreneurship, and public policy now leadership. Stronger application of skills without losing the theoretical core is also important. So this is what the skills building is all about. Multidimensional professionals who have technical skills, communication skills, social skills, global awareness, leadership skills, and intercultural competence, national, ethnic, religious, etc. This is what we're doing with our students. But the trends are the following. This is what we see coming, and this is what we're all doing in different levels of focus and effort. Clearly, the experiential learning. We've all have moved into this domain. There are internships. There are competitions. There are challenge prizes, service. Even we have people doing startups, taking a leave from the university and taking 1 or 2 year students who are doing their own ventures, and then they come back to close the degree out. We have students who are working with NGOs that I would say even 10 years ago we were not working with NGOs. And then we have inductive learning, project-based learning, inquiry case-based, expose students to design before fundamentals. Now design is so key. It's the most key thing. You can teach design to an elementary kid. And you can bring that all the way up through the curriculum, K through 12, all the way to where we are. It hasn't been done, but it's starting to be done now with Engineering is Elementary, which is a program that came out of Boston. Service learning, of course, exposing students to service learning, use of technology such as flipped classrooms and blended learning, the deployment of engineering education research, which we haven't really seen that really get deployed yet, but it will eventually. It's coming, right? It's coming. And then how do we assess authentically and get new information about the students' learning needs? So let me give you a couple examples that we at least done at Maryland, and I'm sure you've done elsewhere. Examples of trends in experiential learning activities. So obviously we all do a hackathon, student competition, a challenge prize project that many of us in this room are working on right now, and a student-run incubator that's open-ended, and then a class that we were teaching called Engineering for Social Change. So here's an all-female hackathon that we did late last year in November. And it was an idea that came up by all our female students who essentially want to reach out to K through 12 in our middle school and high school young women and get them to get interested in STEM, computer science and engineering. And they held a 800-person hackathon, which was fantastic, in one of our basketball gyms. And so this galvanizes interest, even though we lose a lot of the young women before they even get to middle school. This has really been a recruitment tool for us. But more importantly, it's been also an inclusive tool for us in terms of getting our own female students to be going after and serving as ambassadors for the field of engineering and computer science. Again, we talked about this. Solar Decathlon is one of those large-scale, big, outside the experiential learning environment, and essentially involves more than just engineering. So there are people from the business school, people from science, people from public policy, people from architecture who partner on these projects. But these are great outside the class, and they're hard work, but they're so rewarding for the students. And they do it because of, again, the social connectivity. This was a net zero. These competitions are net zero off-the-grid kind of facilities. And then what we did is we sold this house to one of the leading energy firms in our region, and now they have it as a model, and they put new technology in it, and they showcase it to the rest of the community. So it's kind of a nice way to leave a lasting legacy as well. Hyperloop. How many people have teams of Hyperloop teams? I know you do for Purdue, at UC Irvine, and at Texas, and I think you have 2 teams, or maybe more. And so that's happening today. That's why I put it up here. I knew it would be timely. So this is one of those challenge prize competitions that our students, for some reason, just resonate with. I don't know what causes them to get so excited about these projects. But I'll tell you how this one really started. In 2013, Elon Musk, who, as you know, is the CEO of Tesla and SpaceX and other firms, he wrote a white paper, put it on the web, and it had over 2 million downloads. And he realized he had something, that there was interest in his concept of Hyperloop. Then he decided to leverage that interest into a design study. And over 1,000 designs came in. And then there was a preliminary competition at Texas A&M in which 120 teams, mostly university teams from around the world, not just the United States, were then down-selected to about 26 teams, of which UC Irvine, Purdue, Texas A&M, University of Maryland, a few other schools are there today competing with their pod. And this is the kind of thing that galvanizes our students to do it. It's so expensive. Now, it's expensive. I can't share your costs, but it's expensive. But we do it because our students want to do it. Now, here's another simple idea. A group of students came to me one day and said, hey, can you just give us some space? We have our own ideas for mobile apps and whatever we want to do. We just want space to talk to one another. So we want to run our own space. Now, this is really crazy for Dean. I don't give any space away that easily. And it turned out to be like 3,000 square feet of space. right? I'm like, you really what are you going to use it for? This is like four or 5 years ago. And they said, we're going to call it Startup Show. We just need some entrepreneurs and residents to support us, blah, blah, blah. So it turned out this was the best thing I probably ever did. Give them space, let them create. And these are two startups that they created. A 3D printing firm that sells 10,000 units a month for $300, right? M3D. It's based in Maryland, Fulton, Maryland. And this guy named Ben Simon came up with an incredible social idea by being a student. So essentially, in the cafeteria at all of our institutions, the food is wasted every night, every day of the year. And he asked them how much food was wasted, how many pounds of food did you guys just throw away in the garbage? I didn't want to give you the number, it's so ridiculous. And it happens at every school in the country. He decided to take the food from our university down to the D.C. kitchen for homeless people and do it every day. He decided to create, it's like Engineers Without Borders. He calls it the Food Recovery Network. There are now 222 chapters around the nation, and this was only 4 years ago. That's how quickly this went. So our students are incredible. Give them the space, let them create. This wasn't even an engineering student. It was a government and politics student who did this, but he had a whole bunch of engineering students around him. But so it's a little idea. Doesn't take you much to do. Give them the space. Here's another cool idea that we started about 3 years ago. One of our faculty came in mechanical engineering. Devinder Anand used to be the former chair of mechanical engineering at Maryland. Wanted to find a way to connect engineers with philanthropy and social change and entrepreneurship. And he wanted to have a course that not only engineers took, but the whole campus took, and that he could bring these disparate groups together and then have a foundation fund the ideas that are in partnership with a community engagement. So students work with a community to develop an innovative solution to a problem that the community has. Then they pitch the idea to the foundation as part of the end game of the course, and then they fund it. And so the first inaugural winner was this group called Fresh Farm Markets. The inaugural recipient of an Engineering for Social Change grant will use the award for their food prints program, an educational program that integrates gardening, cooking, and nutrition education into the food desert of D.C. and five D.C. public schools. And it's a wonderful idea and a way to use engineering and social change and entrepreneurship for good. It's great. I mean, so he wrote a book on it. And then basically what he's done is he's summarized all the projects over the last 3 or 4 years that they've done. And he would be, very happy to share the curriculum with anyone. I think he shared it with the Big Ten Plus team previously. So, again, not that hard to do, but it turns out it's in high demand now. I don't know how we're going to even cover all the sections because all the people in the university want to take it. So I want to talk now next about, and I know I'm going to go over time a little bit, but I think it's important. Who are we educating? We're primarily educating these millennials and Gen Z. They're different than me and you in this room. They're different work ethics, career expectations, management styles, social consciousness, and connectedness. And their knowledge of technology is way more than mine and yours in the room. They want to see significant change in their lives, and they want it quickly. They want to work on projects that inspire and have a social impact. I mean, that's this generation. It's actually kind of fascinating. We all get to deal with them, so we're very fortunate. So I like to put it in this generational continuum. So I'm part of the baby boomers. Many in this room are part of the baby boomers, so you know who you are. And there are some of you, maybe from part of the Generation X. You're also in this room. And there's very few of you are in the next group, right? And here's the difference. These folks were born with technology. You were not. Maybe some of them had that while they were in the womb, but I doubt it. But you know what I mean. They are digital natives. We are digital neophytes. And some of us still are writing on typewriters. I'm serious. Some of my faculty are still sending me things on typewriters. It's unbelievable. Unbelievable. So what is with this type of student? What are they all about? They're digital natives, so we have to understand that. They use online tools, blogs, social networks. They're always online. My daughter, who's 20, my son, who's 18, they drive me nuts. They're always online. They drive me nuts. I'm sure they drive you nuts. The millennials, they're connected. They're confident, they're connected, they're open to change, they're socially conscious, they love EWB, alternative spring break, anything that has social relevance to do good. They want to make a difference with their knowledge, the skills that they get from your schools and in my school. They multitask like crazy. I mean, I watch my daughter do 5 things. Like, what are you doing? You can't do 5 things really, really well. It's impossible, but she does it. They're comfortable with ubiquitous mobile devices and software. We have all kinds of devices, right? So we have to use this in engineering education because that's what they do. So there's this disruption coming. You all know about it. This is what you and I got. This is what I got at UC Berkeley with Dan. Dan did okay, by the way, just to let you know. Just kidding. This is today's education. We have some online lectures with interactive video, books supplement with faculty lecture notes. Homework is typically online. Exams are in classroom still. Technologies like clickers and tablets are slightly outdated already. Learning management systems have evolved, but now we have much better stuff. So tomorrow's education, all lectures are online with blended learning, automated assessments of student performance, flipped classroom environments, peer-to-peer mentoring and conversations, and instructional coaches are faculty and others. And then, of course, I've already mentioned the experiential project-based learning, learn by doing, and, of course, MOOCs will enhance some learning outcomes. So learning is in a transition. That's how I like to see it. You know, we had self-paced learning that we may have grew up in, instructional design, faculty member at the board, content development. Now we have self-service guided learning when we need it, on demand, right? It's on demand now. It's interesting. It's really interesting, on demand. I can get knowledge when I want it. We have the emergence of, content capture. We have the emergence of virtual and online laboratories. I mean, this is a really emerging space in engineering education, but in general. We also have the emergence of e-portfolios. I can create a portfolio of myself, of what I've done in the past, and make it available to people in engineering. I can do that if I'm a freshman, if I'm a senior high school student, if we in our admissions process use e-portfolios, so you can get a better knowledge of what capabilities I have to come to your school. We haven't gone that way that far, but it's emerging. So the future of learning will be characterized, according to Michael Auer from Austria, open content, open technology, open knowledge for all. By making educational assets free, open, and accessible, the open education movement is beginning to radically change the ecology and economics of education and engineering education, possibly. And, it's still emerging. We're still trying to figure this out, just like everybody was nervous when MOOCs came out in 2012, and most university presidents panicked. Like, should we do it? Sure. I mean, but at that time, you can imagine there were, especially in the liberal arts area, people were really panic-stricken. Like, is our university going to be around in 4 or 5 more years? Residential universities, like most of our comprehensive schools, especially with the focus on STEM or engineering specifically, there's no way we're going away. We have team-based projects. Students are going to always stay together, but we can leverage this new modality of learning to enhance the outcomes for our students. So we see this continuum of relatively common things that we can do today, instructional videos, peer-to-peer academic support, but now relatively skirted, moving towards automated assessment and student design tools. I mean, this is a chart from Coursera and Daphne Kohler, who is really kind of motivating where the future might be heading. And then we can add data analytics to monitor student behavior and performance, and also faculty behavior and performance, because let's not forget that. It's also important. So where are we? It's not like we couldn't do some of this before. There was, if you remember, MIT back in the late 90s had OpenCourseWare. It was funny. It had OpenCourseWare, curriculum, syllabi, problems were online on MIT's Athena website. You remember that, Carl? Nobody used it. It was ahead of its time almost. It was ahead of its time. The web-based services were not ready to handle it. It was there. It's all there. We were ready to handle it. So fast forward to today, where we have better tools, better software, revolution in computing. We now can use all that information freely, and there are interfaces that are very simple instead of complicated, and that's why you see things emerging from Stanford and MIT. and Coursera and Udacity and all these different firms that have started to now make a profit, but also to make our jobs a little bit easier in terms of our outcomes. So I think we see this emerging. So now let's think about what would be some possible online courses that we in engineering might care about. Fundamental math and science, maybe they could be online. Maybe you don't need to be sitting in a 300-person lecture hall anymore, but maybe you do. Depends on the person. Statics or engineering mechanics, mechanics of materials, dynamics, engineering design may not be possible. Maybe, may not. The design is one of those creative things that maybe it's in an integrated environment. Entrepreneurship. We put entrepreneurship online, and now we've had 500,000 students take this course by James Green on developing innovative ideas for real companies. So it can be done, and people could do complete. So more specifically, this is a course from Georgia Tech. It's online. It's a MOOC. It's also integrated back into Dr. Whiteman's class in, I think he's in civil engineering, and in mechanics, sorry. He's in one of the mechanics departments, that's right. And he has integrated this course back into his lecture to give more in-class time room to have discussion. And where they see the lectures online, they have more discussion in the blended learning capacity, and it's worked pretty well for him and for Georgia Tech. So there are very few engineering courses that are in this MOOCs environment. I would say it's only 10% of Coursera. 10% of Coursera. The others are computer science and philosophy and other courses and history and so forth and so on. But engineering has not come to this in terms of quickly to have a large volume. Here's the other thing you might not be aware of that's going on. There are virtual laboratories now, and there's a network of virtual laboratories in which if you're like at a school that doesn't have the money to do laboratories, but you want to have an integrated laboratory, somewhat virtual experience, you can leverage this network to actually teach mechanics labs, materials labs, dynamics labs, right? It is possible. It's still evolving, but there's a global network of these laboratories now that you can integrate into your curriculum and essentially literally do your entire class online, have your students go online to the location, run a particular experiment, get the data back, and then report out on that data, but it was a virtual lab. They were not physically present in the lab. It's really neat. So where does that lead us? Believe it or not, there are now 2 schools in the United States that offer a fully online undergraduate engineering ABET accredited programs. And of course, they started in electrical engineering. Arizona State University, first BS program in electrical engineering that is offered 100% online. Why? Because of that enrollment problem I showed you earlier in my very first chart. Their enrollment at Arizona State, I think their total enrollment is over 12,000 students, I think, if I'm correct. I might be a little bit off of that number. I think it's even higher. And so in electrical engineering, they had 2,000 students in electrical engineering. There was no way they could handle the load without moving to this modality. So they have two degree programs, well, 1 degree program, but you could choose the cheaper BS program online, or you could do the residential program, your choice. Is this where we're headed? I leave it to you. SUNY Oswego also has an electrical engineering that's completely online, ABET accredited. First students just came out this past year. Are these ABET accredited online programs an anomaly, or where the pendulum is swinging? How do professional societies contribute to this emerging trend? Well, you should be a part of it. This is very important. This is an emerging trend. So what does Dr. Gary May from Georgia Tech say? I pick on Gary because he's a good friend of mine, a good friend of a lot of us in this room. And he says, challenges for online engineering education. Pedagogy. MOOCs offer a huge opportunity to investigate how to use technology more effectively, educate students, and improve learning outcomes, retention and graduation rates. I believe that is true. Optimal education requires interaction between student and teacher, and no professor can service 100,000 students in a MOOC. So that's a problem for us. Lab experience and connection to practice. In fields such as engineering or medicine, hands-on laboratory experience are crucial. We would all agree. I think all of us in this room would agree. So how do we do that? That doesn't mean that we can't do some things online, but obviously these design experiences, experiential experiences, they have to be done together in the residential environment. And then there is some issue with cheating. Right now, cheating is virtually impossible to prevent in the online world. It is going to happen. It does happen. So what is the role of professional societies as this new paradigm evolves in engineering education? That's a question for you to answer. So what are the opportunities for collaboration with professional societies? So strategic and university collaborative, defining the actual real-world challenges that require innovative solutions and partner with universities and their engineering education programs. Student-directed hands-on learning experiences, so annual competition, you already do many of these, SAE car competition, there are many others that are like that. Our capstone, obviously design, advice, guidance, critical review at all levels of from first year to fourth year. And then the new emerging competency-based education, which I didn't talk about before until now. So what has been happening in education and in the workforce is that many corporations are trying to do a couple of things. It's really interesting, actually. They want to hire employees that have already been trained in their software or their tools. So they want to have a relationship with universities now where they offer a 5-course sequence in whatever, Microsoft courses, and they want you to buy into that. And I'm not picking on anyone. I'm just saying this is what's happening. So that when a student comes from Purdue or NC State or UC Irvine or Georgia Tech or University of Maryland or Texas A&M, they already have these 5 courses, so they don't have to pay for that. You already paid for it, or they paid for it. So there is this emerging competency-based training thing that's going on out there, and a few other corporations on the list here are actually doing it. But what about a professional society-based course series, where professional societies now are providing some skills that our students need to know in, say, standards and codes, right? They are always changing, but this is a way to use, again, online education and technology to create a competency and make it available. That's something I think engineering education and universities would care about and maybe even actually integrate. So something, again, for you to think about. So in summary, I'm just a little bit over time. There is exponential interest in our field. We are just lucky to be at this time on the planet where the field of engineering is in everything. It's quite exciting. And there's a revolution in computing going with it in parallel. So engineering CS jobs are in high demand with very good salaries, and we're grateful for that. A new normal is evolving in engineering education. The value proposition, as Dr. Mote likes to say, creation, solutions, humanity, and society, connected to what people understand. So there's a greater emphasis on hands-on and experiential learning opportunities in context of current and future societal grand challenges. Technology and active learning methods can enhance student outcomes. And professional societies play a critical role in all of this. So your role is connecting engineering education to real-world practice and solutions, serving as design team reviewers, mentors, advisors, lecturers, educators. We have now more professors of the practice than ever before in our universities. We have more instructional faculty than ever before because of the high demand of the enrollment. And these are primarily coming from people from practice. Creating challenge-focused projects like Hyperloop to advance technology and skills development. Will Hyperloop be the next revolution in transportation? I don't know, but I know it got a lot of our students interested in doing it. So providing opportunities for international and service learning. I think societies play a role in that as well. And then more importantly, which we did not have a time to talk about, and I chair the K-12 EDC committee, is serving as ambassadors to the profession with respect to outreach to K-12. It's so important. I mean, we've been working on this AP in engineering, and we've made some progress, but we've kind of slowed down a bit, and it's a big deal. Engineering should be part of the core language of education. It should be part of the core, not a fringe topic, part of the core, like history and English. Not a fringe topic, a core topic. Every student should take engineering. That's one reason why we're trying to do this AP in engineering. We're just trying to change the equation so that they have to talk about us. And we're making progress, but we're still not there. So anyway, I want to thank you, Dr. Mote and Leah Jameson. Thank you very much for inviting me. Some final thoughts. The enterprise that does not innovate inevitably ages and declines, and in the period of rapid change such as the present, the decline will be very fast. And then I always like to say engineering education must continue to evolve into a new normal to ensure U.S. competitiveness in a rapidly changing world. So thank you, and I'd be happy to answer any questions. Okay.
I'm ready. So you highlighted tremendous growth, and that's something that we've been talking about here, and we've seen it. We all know that that's the case. The flip side of that is if you look at what the engineering programs are actually doing, right, we're actually staffing up now like crazy.
Right.
There are these huge searches for large numbers of faculty over all engineering regions in the country.
Yep.
I mean, and large numbers of growth of new faculty. I contend that that is connected to an old model and is actually opposite of the directions in which you've highlighted here. And our problem is that funding streams, federal funding streams, government funding streams, state funding streams, and industry funding streams won't be there to support those larger numbers of faculty when they actually become entrenched in their programs.
Agreed.
So can you talk a little bit about that?
Well, I believe that you're spot on. I believe that there's a new model of engineering education in terms of faculty makeup that's also evolving. So I did an analysis of the Big Ten schools, and over the last 5 to 10 years, while some schools have grown in tenure track faculty, they've really tripled or doubled in instructional or research faculty. In those categories, we now have huge cadres of adjunct and or instructional and or research faculty, and I believe that is probably the model that's more survivable. Because if you hire tenure track in research one institutions, you're right, there's a limited amount of funding. There's only it just becomes more competitive. And of course, the climate currently is uncertain as to where the direction of the country is going in terms of research. So it could be, you have to be careful with the tenure track faculty hires. I think the instructional faculty hires, on the other hand, can service the large enrollment that we have in our schools.
Linda Katech from UC Davis. Darryll, I really enjoyed your presentation. A comment I would like to make is that if we look at the number of women in engineering, and if you not necessarily only look at the U.S. numbers, but you look at the overall participation, you will see that those numbers have not necessarily increased over time. That I remember when I was at the University of Michigan mid-90s, towards 2000, we would see the numbers to go, and I believe there was a time when the averages were close to like 24%, 25%. Since then, you look at the total numbers, the numbers have gone down at a time when women's participation in higher education has really increased tremendously. In many universities, UC Davis included, we have now more than 56%, close to 60% of students are women on the university campus. And if you look at the science fields, in some of them, women's participation is close to 50%. So considering that the numbers of women who are going for higher education have increased substantially during that period of time, I think engineering has not done very well in making women becoming excited with the kinds of changes, as you say. It's exciting time to be an engineer, but I don't think women really share that kind of point of view. And that inability to attract more women, I think, will eventually in the future compromise our ability to participate in solving important social problems. And the last comment is that with the fourth industrial revolution that everybody is speaking about, my fear is that we're going to still leave women and underrepresented minorities behind. And that will only grow the digital divide between those who have and those who don't. And in the past, that has shown that it has not really led us into, better times for everybody. So,
I mean, I agree with your comment. I think, connecting engineering to these societal challenges and to the social problems that our country faces and that society faces tends to bring more women to the table. I would tell you that that's definitely true. We see it with our Engineers Without Borders. We see it with other problems that are more socially connected. They come into engineering. For example, this course on engineering for social change, it turned out that course was 70% women and 30% men. So it brings, I can't make a broad sweep about this issue, but I think we have to find ways to engage that population group so that they stay in engineering and make the problems that more to the liking that they care about to help solve. And I think when we do that, we'll make a dent. Now, something that Leah has done at Purdue is one of the studies that Purdue has done has showed that if you look at the admissions criteria and you track leadership of the incoming applicants and say it's a female students incoming applicants, if they have leadership in their background, they tend to do well in engineering. And she's shown that that's an increase in enrollment due to tracking leadership skills from the applicant pool who are successful. So we can use some techniques to increase the numbers, but there's one real big issue. We're losing half of the population in middle school. So part of the problem we don't control, we in higher education, but we should care about a lot because it's controlled through K through 12. So I think we have to go backwards and actually go really correct it there as well.
So Darryll, I really liked your talk. I think Dan did a good job mentoring you through your engineering career, and I'm sure he's very proud of you. I wanted to mention a question that Greg Washington raised with me 5 years ago in a National Science Foundation Committee of Visitors thing that I chaired, and he was on the committee. And he said, I think what we need to do is we need to he said, I think we ought to have some BAGs, some big goals. And one of them should be to cut the cost of education in half and cut the time for an engineering degree in half. And it seems to me that you have presented let's say, the elements of a pathway that could exist at some point in the future, especially with the ABET approvals, which we never anticipated 5 years ago, and some of the other things going on. So I just want to thank you for that because it's sort of an eye-opener. And then I have a question, which is, as we look at these challenges with respect to creating visibility for engineering, developing our brand, building diversity and all those kinds of things, and the excitement of engineering and the financial gains that can come from it, they're kind of all there. And so my question really is, what are your thoughts on you show that baby working on the telephone and everything. I mean, why can't engineering be taught in, let's say, K through 3 or K through 4? I mean, what are the possibilities of starting of going way back in the pipeline? Because we come into the pipeline, particularly NSF at the undergraduate level, and that is way late when people, their attitudes are already defined, their pathways are not finalized, but they have ideas by the time they go to school of what course they're going to pursue. And so we're way late to affect that decision. And what could we do about that?
So I think it goes back to the statement that Dan kind of made to me, which was engineering has to become part of core education, K through 12, not a fringe topic. So, for example, the sort of engineering is elementary program, which now I think is in, thousands of schools, K through 5, is essentially about teaching the engineering habits of mind concepts to elementary students and getting them thinking about design and making and getting them connected to creativity even. And so I think it's going to be a long process of really redoing K through 12, partnering with colleges of education to start producing teachers who have credentials that have a specialty in engineering that they can go out and teach in middle school, elementary school, and in high school. I think we have a long process to change that equation while also changing the conversation that National Academies of Engineering has created a report on to help communicate our field to the rest of society. We do a terrible job, and we can't even do it to ourselves in terms of communicating. So I think, the next generation science standards has helped us hugely to put engineering as part of that framework. And now it's up to us, all of us in this room, not any one person, to help go back and implement those strategies in the curriculum. I know we're out of time. Thank you.